Hello, this is Ms. DB, and in this lesson we are going to learn about logarithmic functions. We call these log or log functions for short. This is from Chapter 7, Section 3. So our objectives are to write equivalent forms for exponential and logarithmic functions and to write, evaluate, and graph log functions. Here's an example of kind of approaching why we need log functions. Let's say that you were wondering how many times you would have to double $1 before you had $8. You could use an exponential equation to model this situation. The 1 is how much the dollar is worth times 2, because we're doubling, to the x power. That would be equal to 8 because our goal is to get to $8. So really we're just saying 2 to the x equals 8. And the question is, what would x be? And you might say, well, I know that 2 to the 1 is $2, and 2 to the second power is $4, and 2 to the third power is 8. So if the exponent was 3, then I would have $8. So if I doubled the dollar 3 times, I would have $8. A logarithm is a way of figuring out what the exponent is. Here's an even harder question. This is supposed to say 512 here. If I wanted to know how many times I'd have to double $1 before I had $512. So we could solve this with the exponential equation 2 to the x equals 512. You can still do this in your head, but it gets a little trickier because you may not know 2 to the what power equals 512. But using a logarithm is a way to write this so that we will find what the exponent is. So it's an inverse operation to an exponential equation. All right, so this right here, this is our definition of logarithm. You will want to write this down on a post-it note or a piece of paper and tape it next to your table where you work on your math at, because you can refer back to this and pretty soon you'll have it memorized. But at the beginning you want to make sure that when you write your exponential equation into logarithmic form or your log into exponential form, that you put all of the numbers in the right spots. We read, this side we read as b to the x equals a. This side we would say log base b of a equals x, or is x. And you'll see that the exponent in the exponential form is equal to the answer in log form. So the answer of a log is an exponent. Remember that. All right, so the first thing that we are going to do is we are going to practice writing exponential equations in log form. So what we need to do is keep an eye on our definition up here that shows us how to go from one to the other. And the more you practice this, the better you'll get. But for the beginning, we'll just keep an eye on this. So the 5 I wrote in red. Yep, the rest are in red. And I'm going to put all of the bases, the b's, in green, just so I can look at the color coding. Now you of course do not have to use different colored pencils or markers or even fonts when you are working on this, but you might find it helpful. Whoops. You might find it helpful when you're learning it to remember that these colors will match up with the definition up above. I'll just underline that this is the A's are blue. All right, so the first problem says that we have 3 to the 5th equal 243. So 3, that's our base, 5 is our exponent, and it's equal to our A, which is 243. So we need to just rewrite that in the log form. It would be log base 3, there's the 243, will be equal to 5. It's always equal to the exponent. The second one, 25 to the 1/2 power, is equal to 5. Our exponents can be fractions, and the exponent will be the answer to the logarithm. So log base 25 of 5 is equal to 1/2. In the next one, we have 10 to the 4th equal 10,000. Remember that our exponent will be the 4. That's our answer to our log. This would be log base 10 of 10,000 is equal to 4. Now the next one, we have a negative exponent, and that's okay. You can have negative exponents, or in this case, a negative log. Our answer to a log can be negative. And finally, we just have variables in the last one, and that's okay. You can still rewrite it as a log even if they're all variables. This would be log base A of C is equal to B. For this slide, I want you to pause the video, try these problems on your own paper, and then check and see if you were correctly able to write them in logarithmic form. Okay, so let's check your answers. The first one you should have written as log base 9 of 81 is equal to 2. When you after you write log, that's just a full-size regular word. The 9 is called a subscript. So you write that smaller and a little bit below the word log. And then 81 is just a normal number again after that. On the keyboard, if you're using Word, you're probably used to seeing where you make exponents with the x squared button. Next to that, there is a subscript button, which the 2 is below and to the right and kind of low down next to the x. That's the button that you will use to make your base on the Word documents. All right, the next one, 3 to the third is equal to 27. You would write that as log base 3 of 27 is equal to 3. And now the last one, we know that anything to the 0 power equals 1. So in exponential form, this should make sense to you. Yep, it doesn't matter what x is because anything to the 0 power equals 1. As a log, if you have the log of 1, it will always be equal to 0 no matter what the base is. No matter what x is, if it's the log base anything of 1, it's equal to 0. So the log of 1 equals 0 all the time. Now we're going to look at going the other way. We're going to start with our log form over here, and we're going to rewrite it as our exponential form. So we are going to start off with log base 9, and if you want, you could color code these. So let's see, all of our exponents are red. They have all of them except one already red. And our green is our base. So these subscripted little numbers here, these are all of our b's. This would be 8, 4, and that's b. And then our a's are what we're taking the log of. Those are those numbers here. All right, so let's look at how we would write log base 9 of 9 equals 1 as an exponential equation. It would be 9 to the 1 power, because 1 is the exponent, equals 9. And that makes perfect sense because anything raised to a power of 1 is equal to itself. The next one, you would have 2 to the 9th power is equal to 512. Remember the base, which are the little green numbers that are next to the log, these numbers will be here, and then it's raised to the exponent equals 512. The third one, our base is 8, and it'll be raised to the 1/3 power. So 8 to the 1/3 is 2. That's the same, by the way, as saying we have the cubed root of 8. That's just another way of writing it, 8 to the 1/3. In the next problem, we would have a base of 4, an exponent of -2, and then that will be equal to 1/16. 4 to the -2 is 1/16. A log can be a negative number, and an exponent can be negative. And then the last one, this is similar to what we looked at before. Anything, any base to the 0 power is equal to 1. So b to the 0 equals 1. All right, here's some for you to practice. Again, pause the video, try these problems on your own paper, and then resume the video and check and see how you did. You should have found that the first problem was 10 to the 1 equals 10. That in the second one, you should have gotten that 12 to the 2nd power equals 144. And in the last problem, we have a fraction as a base, which is fine. You can have that. 1/2 to the -3 power is equal to 8. Note that the 1/2 should be put in parentheses like that, because that if you just wrote 1/2 to the -3rd, you might think it's just 1 to the -3rd instead of the whole fraction being raised to the -3 power. On your worksheet, you're going to be doing several problems just like what we just practiced, where you are going to change from exponential form into log form, or from log form into exponential form. In number 6, I didn't talk about this yet, but we will in the next slide. If there is no base listed, it's a base of 10. And we'll talk about that in a minute, but that's called a common log. So when you do number 6, the base is 10. And so here's our 10. And our x, of course, is 3. And that will be equal to the a of 1,000. And that makes sense. When you rewrite it, it should make sense. 10 to the third power is equal to 1,000 because 10 times 10 times 10 equals 1,000. In number 7, to complete this table, first of all, A is already done. 7A is completed. For B, you're going to change this exponential form into log form. And for C, you'll change the log form to exponential form. So you just need to look at what's missing and then know whether you have to convert from exponential to log or log to exponential. There are some special properties for logarithms, and we looked at some of those already in our examples. If you have log base b of b, you will get 1. And we looked at that in an example. We had log base 10 of 10, and we rewrote that in exponential form, and you'll see that that would be 10 to the 1 power equals 10, which makes perfect sense that anything raised to the 1 power is equal to itself. So anytime that you have the base equal to what you're taking the log of, it will be equal to 1. So for example, log base 2 of 2 would equal 1. Or log base 7 of 7 will equal 1. There's another special property that says that if you are taking the log of 1, you will get 0, no matter what your base is. So it doesn't matter if you have log of 30. If you're taking the log base 30 of 1, it will be equal of 0. It'll be equal to 0. And the reason is, in exponential form, when you rewrite it, you would get b to the 0 equals 1. Anything to the 0 power is 1. So 30 to the 0 power is 1. Or if you had log base 2 of 1, that would still be 0 because 2 to the 0 power is also 1. Anything to the 0 power is 1. And here we go, what I hinted at before. If you have a log with base 10, we call that a common logarithm. So anytime you see a problem that does not have the base given to you, you can assume that that is 10, that is the common log. If you see log 5, that means log base 10 of 5. So in that problem earlier on the worksheet, we were assuming that that was a base 10. Your calculator can do logs that have base 10 only. We will learn in a couple sections what to do if you have a different base than 10 and you need to evaluate it or graph it. But your graphing calculators, your scientific calculators, Desmo, Sketchpad, can only handle log base 10, but they just say log when you're looking at them. They don't say log base 10. They're using the common log of just log. You can use mental math to evaluate some logarithms, no matter what their base is. For example, this one is going to be base 10 because it doesn't list the base, so we assume it to be the common log. But what is, let me put the base in here. We're really saying if we have log base 10 of 0.01, what does that equal? What is our exponent? What is our answer? So if I wrote this in exponential form, I would say 10 to the what power is equal to 0.01. And maybe you don't know that right away. Maybe you're like, well, I know what 10 squared is. 10 squared is 100. These are, if it asks you to do mental math, you're going to get an integer answer. An integer is like 1, 2, 3, and all of its opposites, 0, 1, 2, 3, and -1, -2, -3, and so on. 10 to the 1 power is 10. 10 to the 0 power is 1. I don't mean that to look like a negative there. What about 10 to the negative 1? 10 to the negative 1, a negative exponent, tells us to drop that down and make it into a fraction. So that would be 1/10, which is the same as 0.1. 10 to the negative 2 would be 1 over 10 squared, which is the same as 1 over 100, which is the same as 0.01, which is what we're looking for here. So the answer to this would be -2, because 10 to the negative 2 is equal to 0.01. So the log of 0.01 is equal to -2. So make sure when you're doing this, when you're thinking about it and maybe rewriting it, that you know that the answer, what we're looking for here, is the -2, the exponent. Remember, when you're looking for a log, you're looking for the exponent. This one, they tell us that the base is 5, so let's rewrite this in exponential form so we can make a little more sense of it. That would mean that we have 5 as our base to what power is equal to 125. And again, you might off on your paper say, well, I know 5 to the 1 power is 5. 5 squared is 25. It's greater than 1, so I know that the answer is going to be a positive. And it turns out that 25 times 5 times 5 is 125. So the exponent is 3, the missing exponent, which means that the log base 5 of 125 is equal to 3. You can have a fraction, and this isn't too hard either. If we are going to rewrite it in exponential form, we're asking ourselves 5 to the what power would be equal to 1/5. And the answer would be, we looked at it earlier, if it was -1. If we had 5 to the -1, that's 1/5, because the negative exponent tells you to drop that down into the denominator. So the log base 5 of 1/5 is equal to -1. These are just some more problems to practice. If we have a decimal, 1, 2, 3, 4 zeros here, you might have to think about it a little bit. You might even have to try it on your calculator. Maybe you know it's going to be a negative exponent. Maybe you want to try 10 to the -2, and you'll find that's not enough. Maybe you try 10 to the -3, and they forgot some of their zeros here. And then you might eventually try 10 to the -5, and you'll find, yes, that's exactly right. Or you can go 1, 2, 3, 4, 5 decimal places is going to match up with our exponent. So after you do a few of these, you might notice that there's a pattern there. This one's a little tricky too, because we don't tend to think with, if we put an exponent here, we know it's going to be negative, but we're getting instead of a fraction, we're getting this decimal answer. It would be more helpful here if they wrote 0.04 as its fraction, which is 1/25. And then you might quickly be able to tell that this is -1 is the answer. You might have to get your calculator out to double check what you're doing on something like that. All right, on your worksheet, you're going to do some problems where you're going to use mental math to evaluate. Remember that all of these answers will be integer answers. There won't be any decimals. Some of them could be negative though. In number 19, this is not log base 10, it's log base 100. So we're saying 100 to what power is equal to 100 million. So you might want to get your calculator out again and check what's 100 squared, what's 100 cubed, and see if you can find your answer. So on all of these, it might help you to write that these are equal to x or equal to question mark, and then to rewrite them in exponential form, and then to find the missing exponent that you are looking for. Remember that if there is no base, like in 13, 14, 15, or they already have, that would mean base 10, and 24 as well. Those are common logs. All right, let's look at finding the inverse of logs, or the inverse of exponential functions. So if we graphed y equals 2 to the x, this exponential function, we would get a graph that looks like this. And we know from the last section that if they are inverses, they are going to be symmetric about the line y equals x. That's what this green dashed line is. So the inverse to it is this red line. And I'll go through the steps here, but the inverse of y equals 2 to the x is y equals log base 2 of x. So these are inverses of each other. the exponential, and the log. The domain of the exponential function, the original function, is all real numbers, as is the range of the log function, the inverse. The range of our exponential function, our original, is that y is going to be greater than 0, as is the domain, x is going to be greater than 0, the domain in the log function. So just like we learned in our last section, the domains and range kind of crisscross each other. All right, this is on your worksheet, but I want to go through how we would find the inverse function of an exponential function or of a logarithm. So this should be either one, or an exponential. All right, so we have f of x equals 4 to the x power. First step is to rewrite the f of x as just y. Replace f of x with y. So now we have y equals 4 to the x. Second step, switch the x and y. Put the x here where the y was, put the y here where the x was. Then I just rewrote it so that on the left side I had 4 to the y, so it matches my format up here. Don't have to do that step, but it kind of helps me keep everything straight. And I color-coded it so we could match up what is a, what is b, what is x. All right, next I'm going to solve this for y. So to solve this for y, I'm going to just change it to logarithmic form. So my base is 4, so I write log base 4. My y is my exponent, so that's going to go over here. And my x is actually my a, so that's going to go right here. Now this, I wrote it here too, that is now solved for y. You might prefer to put the y over here. And then all we need to do next is replace our y with our function notation, which would be f to the negative 1 of x. So that says that this is the inverse. And that's it. And you'll do the same thing for number 10. Let's look at number 11. In number 11, we'll be going from the log to the exponential form. So let's find the inverse of y equals log base 5 of x. All right, so step 1 is already done. The f of x was already changed to y. Let's do step 2. Step 2 says to switch the x and the y. So now we have x equals log base 5 of y. Okay, step 3, solve for y. All we have to do to solve for y is use the definition of a log to rewrite it in the other form. And then we'll automatically have solved this for y. So log base 5, 5 is the b, so I need to write 5 as my base. And then x is the exponent, which is x, equals the number I'm taking the log of, which is the a, or in this case the y. So I have solved this for y. If you prefer, you can flip it so that the y is on the left side. So this is 5 to the x, and in inverse function notation, it would look like this. And that's it. That is how you find the inverse of an exponential or a log function. Graphing log functions are a little bit tricky. Like I said, Sketchpad and Desmos only recognize log base 10. So until we learn the change of base, all we can really do is graph the inverse of its exponential function. So remember that inverses you can find and graph by plotting points. So we have some values, -2, -1, 0, 1, and 2. We plug them in and we got a y value. And then we graphed as close as we can and graphed it on here. Now Desmos or Sketchpad could graph this function, 1.25 to the x power. So you could also just use Sketchpad. But the great thing is that once we have these points, we can use those to graph the inverse. The inverse will have the point x would be 0.64 and y would be -2 as one of my points. So 0.64 is about here, -2 is about here. And then my next point would be at 0.8 and -1. Hey, my point erased. 0.64 and -2. And then I would be at 0.8 and -1. and then I would be at 1 and 0. There's a nice point. So at 1, I'm at 0. And you can see that it's going to kind of go this way. It's going to kind of curve up. On the next page, you can see all those points have been graphed. Oh, I kind of curved the wrong way, and it's going up here. And this is my original function here. And this is the log function. So as they are supposed to be, they are symmetric about the line y equals x. And that is one method you could use to graph a log function, by using its inverse in a table of values. You won't have to do that on, and also find the domain and range. You won't have to do that on the worksheet. Instead, on the worksheet, there's a graph already there for you, and you need to answer a couple questions about that graph and find the domain and the range of both the function and its inverse. As I said before, you can use a calculator with the log key in order to evaluate logarithms. In this problem, it's kind of a word problem where they tell us the pH, or actually this is the hydrogen ion concentrations, and you're going to find the pH using a formula that says you would take negative log of the hydrogen. Now this is log base 10. You don't have to tell your calculator that, because that's what your calculator will automatically find. So all you do is you punch in negative log and then your number and hit equals, and you will get your log value. Now if you're using a handheld calculator, you will punch it in just like this. If you are using a calculator on your computer, let me show you what it'll look like. Instead of punching in log first and then the number, see it right away says you can't have the log of 0. So you have to put the number in first, which is 0.0000. Is there 6 zeros? 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6, 25. I forgot the negative. And then it was supposed to be negative, so I'll change the negative now, because it was supposed to be negative log of that number. So 6.602, so on, so on, so. So I should have pushed the negative. Let's see. I don't think I can. I have to type in the number first. I don't think I can push negative log, so I have to do log, and then I have to hit the negative after on the computer calculator. So if you're using just this little calculator, it's not as smooth as using a handheld scientific calculator. And that's really about it. There was just a couple more examples using different vegetables or fruit or foods on this PowerPoint. So let me know if you have any questions. Have fun with logs, and remember that it's something new, so it's going to require some practice before you get good at it, and that's all right. It's a handy thing to have an inverse of an exponential. It's a good way to be able to find missing exponents. All right, thanks. Have a great day.